All right, let's dive right into a true cosmic detective story. We are on the case of one of the deepest, most baffling mysteries in all of physics. A mystery that puts our two greatest theories of the universe head-to-head. The scene of the crime? A black hole. And the victim? Well, it might just be reality as we know it.
And this, right here, is the question at the heart of our whole investigation. Now, I know what you're thinking. Soul? That sounds a little out there, right? But trust me, framing it this way gets us right to the core of a very real, very scientific puzzle that challenges, well, pretty much everything. So, to be super clear about what we mean by soul here, we're not talking about anything spiritual. In physics, an object's soul is all of its information. The complete quantum blueprint that makes it unique. Every single particle, its structure, its entire past. It's the object's identity. And that is the information we are trying to find.
Okay, so let's establish the basic facts of the case. It all starts with a disappearance, a cosmic one, happening right at the edge of space and time. The event horizon of a black hole? Think of it as the ultimate point of no return. It's not a physical surface, but it's a boundary where gravity becomes so ridiculously strong that nothing, not even light itself, can escape. Once you're in, you are in. End of story. Or is it? And this is where the plot really thickens. You see, we have two star witnesses in this cosmic case, and their stories completely contradict each other. This is the central conflict.
And here they are, our two heavyweights. In one corner, you've got Einstein's general relativity, our champion theory of gravity. And in the other corner, quantum mechanics, the undisputed king of the particle world. One says information can be permanently destroyed. The other says that is absolutely forbidden. They literally can't both be right about this.
So, this is general relativity's star piece of evidence. It's called the no-hair theorem. And what it says is that a black hole is shockingly simple. It doesn't matter if you throw a star, a planet, or a whole library of encyclopedias into it. From the outside, all that unique, detailed information is just gone. It's been shaved off, leaving behind only three things: mass, charge, and spin. According to this, the information is lost.
But then, quantum mechanics steps into the courtroom and objects. It has a core, unbreakable law called unitarity, and you can think of it like this. The universe never, ever forgets. Information can get scrambled, it can get hidden, it can be rearranged in mind-boggling ways, but it can never be deleted from existence. You could, in theory, always rewind the tape and see what happened. The information has to be eternal.
For decades, this was just a weird theoretical argument. Physicists could kind of agree to disagree. But then, one person came along and turned this entire debate from a headache into a full-blown crisis. Let's just quickly trace how we got here. It starts way back in 1915 with Einstein predicting these bizarre objects. For a long time, they were just a curiosity. Then, in the 70s, a physicist named Jacob Bekenstein made this brilliant connection, suggesting a black hole's surface area is a measure of its information. But the real earthquake happened in 1974, thanks to Stephen Hawking.
This was the absolute game changer. Hawking brilliantly applied quantum physics to the edge of a black hole and discovered they're not totally black, they leak. They give off this faint glow we now call Hawking radiation. And here's the kicker. Because it comes from random quantum jitters, this radiation is thermal. It carries no useful information. It's just heat. And over unimaginable stretches of time, this leak causes the black hole to shrink and eventually evaporate into nothing.
So, let's put it all together. The black hole eats an object, swallowing its information. Then, the black hole itself completely disappears, and the only thing left behind is this cloud of random, informationless radiation. So, where did the original soul of that object go? Did it just vanish? Poof? This is the black hole information paradox, and it's a massive violation of quantum mechanics.
Well, this paradox ignited a firestorm in the world of physics that's been raging for decades, sending scientists down some of the most creative, bizarre, and brilliant rabbit holes in the search for a way out.
The proposed solutions sound like they were pulled straight from science fiction. I mean, look at our list of suspects. You have the holographic principle, which says the information gets painted onto the event horizon. There's fuzzball theory, which imagines black holes aren't empty voids at all, but rather tangled messes of string. And then there's the wild ER equals EPR idea, which suggests the information sneaks out through tiny wormholes in spacetime.
Let's just focus on the most famous of these for a second, the holographic principle.
It's a true mind-bender. The idea is that, kind of like how the 2D chip on your credit card can store the info for a 3D hologram, maybe all the information for what falls into a black hole is stored on its 2D surface. This has a staggering implication. Our entire 3D reality could just be a projection. Wild stuff.
So, okay, all of this is fascinating, for sure. But you might be wondering, why should I care? Why are physicists so obsessed with this? Well, it's because the answer digs down to the very foundations of existence.
To put it bluntly, solving this paradox isn't just about understanding weird, distant objects. It's about finding the master blueprint for the universe. The solution, whatever it is, will force us to completely rewrite our most basic rulebook for reality.
So what's at stake? For starters, it makes us ask profound questions, like this one. Is our universe what it seems to be? Could it be that our familiar three-dimensional world is really just an elaborate projection, with the real action happening on some distant two-dimensional surface? Or what about this? Does the universe have a delete button? If information can be truly lost forever, it means the fundamental link between cause and effect can be broken. It would mean the past isn't just hard to decipher, it can be permanently erased as if it never happened.
And finally, it boils down to this. Which of our most trusted laws of the universe has to break? Is Einstein's elegant picture of smooth, curving spacetime fundamentally flawed? Or does quantum mechanics' sacred, untouchable law of information conservation actually have a loophole? Something's got to give. Which brings us right back to where we started. The evidence is in, the witnesses have testified, but the case is far from closed. When that black hole finally evaporates, is an object's unique story, its soul, destroyed forever? Or is it simply translated, scrambled beyond recognition, and then rewritten into the language of the cosmos for something new to emerge? The final verdict is still out.